Have you ever wondered how your phone unlocks with just a glance at your face? Or how social media platforms can automatically tag your friends in photos? The magic behind all this is something called a convolutional neural network, or CNN for short. Today, we're going to dive deep into the world of CNNs and demystify how computers learn to see and understand images, just like we do. So, what exactly is a CNN? Think of it as a special type of artificial brain specifically designed to process visual data. Unlike a regular neural network, which treats all parts of an input equally, ACN is inspired by the human visual cortex. It knows that pixels in an image are arranged in a specific way, and that nearby pixels are more related to each other than pixels that are far apart. This spatial understanding is the key to its power. Let's break down how it works. The first and most important layer is the convolutional layer. Imagine taking a tiny magnifying glass, called a filter or a kernel, and sliding it across the entire image, one small patch at a time. This filter is looking for a specific feature, like a straight edge, a curve, or a particular color. As it slides, it performs a mathematical operation called a convolution, which basically measures how strongly that feature is present in each patch. For example, one filter might be designed to detect vertical lines. When it slides over a part of the image with a tree trunk or the edge of a building, it will light up, signaling a strong match. Another filter might look for horizontal lines, and another for a specific shade of blue. A single convolutional layer can have dozens or even hundreds of these filters, each one searching for a different basic feature. After the convolution, the output is a set of feature maps. Each map highlights where a specific feature was found in the original image. So, one map might show all the vertical edges, and another might show all the green areas. Essentially, we've broken down the complex image into a collection of its simplest components. Next up, these feature maps often go through something called an activation layer, usually using a function called ReLU, which stands for Rectified Linear Unit. Whether an edge is here or a few pixels over, the pooling layer will likely produce the same output. So, a typical CNN starts with a sequence of these three layers: convolution, activation, and pooling. And it doesn't just do this once. It stacks them one after another. The first set of layers might learn to detect very simple features like edges, corners, and colors. The outputs of these layers are then fed into the next set of layers, which combine these simple features to learn more complex ones, like textures, patterns, or simple shapes like eyes and noses. As we go deeper into the network, the features become more and more abstract and complex. Subsequent layers might learn to recognize entire objects like faces, cars, or dogs by combining the features learned in the previous layers. It's a hierarchical process, building up a sophisticated understanding of the image from the ground up, moving from simple pixels to complex concepts. After passing through several of these stacked, convolutional, and pooling layers, the data is finally ready for the grand finale. The multidimensional feature maps are flattened into a single, long vector of numbers. This long list of numbers represents the most important high-level features extracted from the original image. This vector is then fed into a traditional, fully connected neural network, just like the ones you might already be familiar with. For example, if the input was an image of an animal, this part of the network would look at the features that might represent furry texture. It might say, I'm 95% sure this is a cat, 4% sure it's a dog, and 1% sure it's something else. The category with the highest probability is the network's final prediction. So, how does the network learn which filters to use in the convolutional layers? For each image, we let the network make a prediction. Then we compare its prediction to the correct label if it gets it wrong. We calculate the error and use an algorithm called backpropagation to adjust all the tiny parameters inside the network, including the values in the convolutional filters, to make it slightly more accurate next time. It's a bit like a student learning with flashcards. With enough practice and feedback, the network gradually gets better and better until it can accurately classify images it has never seen before. The applications of CNNs are everywhere. In self-driving cars, they analyze real-time video feeds to identify pedestrians, traffic lights, and other vehicles. In medicine, they assist doctors by analyzing medical scans like X-rays and MRIs to detect tumors or other anomalies with incredible accuracy. They're also used in agriculture for monitoring crop health, in security for surveillance systems, and even in art for creating new styles. From simple feature detection to complex object recognition, convolutional neural networks have completely revolutionized the field of computer vision. They've given machines the ability to interpret the visual world in a way that was once pure science fiction. By mimicking the hierarchical nature of our own vision, CNNs have unlocked a powerful new way for us to interact with technology. So, the next time you see a machine understand an image, you'll know the secret behind it, a cascade of convolutions, activations, and pooling, all working together to build a rich, layered understanding of our visual world. The journey from pixels to perception is a fascinating one, and CNNs are at the very heart of it. Thanks so much for watching. If you enjoyed this deep dive into the world of AI, don't forget to hit that like button and subscribe for more content just like this. And if you have any questions or ideas for our next video, drop them in the comments below. See you in the next one.